Okay. Well, good morning, everyone. It's a pleasure to have been invited to participate in this meeting. And what I want to do is speak about the topic of an analytic toolbox for predictive maintenance decisions. Well, we all have heard the term analytics. And here's a nice definition of analytics given by Davenport and Harris. And they say that analytics is the extensive use of data, statistical and quantitative analysis, explanatory and predictive models, and fact-based management to drive decisions and actions. That's their definition of analytics, and I like it. And what I want to do is speak about the application of analytics to optimize condition-based maintenance decisions. And here's a common analogy. We often think of heart failure and ask ourselves the question, what's the risk of someone suffering heart failure? And perhaps it depends on the person's age, and perhaps it depends on the person's risk factors. And so, for example, my age is possibly a risk factor for heart failure, but for young people in the audience, not so important. But there are also risk factors, cholesterol, blood pressure, and so on. And we often want to find out for ourselves what our key risk factors are. Now, when we come to monitoring the health of equipment, it's the same thing. What's the risk of the equipment failing due to some failure mode? Does it depend upon its age? Does it depend on certain risk factors? And if there are risk factors, we want to know what are the risk factors. For example, if we're doing oil sampling, should we pay attention to the rate of change of iron? Should we pay attention to the cumulative value of the iron? Should we pay attention to the absolute value of the iron in the oil sample? There are many, many possibilities. We want to try and find out what the key risk factors are. Now, the way in which I see condition monitoring being carried out in many industries is rooted in statistical process control. So here's a control chart. So we take an oil sample, look for example, the measurements of iron in parts per million. And if it's below 200, we say everything's okay. If it's above 300, we become concerned. And we, of course, don't just have one chart, we often have many charts. So this chart is easy for us to understand, but there are certain limitations. For example, which measurements should we really pay attention to? What are the best limits? What's the effect of age? Can we make a prediction? What about the consequence of a failure? And because of these limitations, what we have developed in my research group at Toronto, along with industry, is a tool that just extends that control chart procedure, which we'll see next. And this new approach is going to ask us to find out what the risk is of the item failing at the time of inspection. We calculate the hazard, and we use a procedure called proportional hazards modeling. And this is what the new control chart looks like. And as we make our inspections, we get results appearing on this chart. So here's what happens. Once inspector makes the inspections, gets the results from the laboratory, from oil sampling, for example, a dot appears on this red, green, and yellow chart. If a dot appears in the green chart, everything is okay. If a dot appears in the red chart, it says a smart move is to plan to do a preventive removal. And this chart takes into account the key risk factors. For this example, it came from a bearing on a pump. And the important risk factors were two vibration monitoring measurements, one in the fifth bandwidth, actually both were in the fifth bandwidth. One was in position 1 in the pump, one was in position 1 in the pump, but in the vertical direction. And the coefficients you see in front of these measurements at the bottom are the weightings to give to these two measurements. Now what I want to do is to show you how to get that red, green, and yellow chart, and then discuss some case studies. There are three keys. First of all, we have to estimate the hazard, the risk of failure. We need to calculate transition probabilities from your data. and we'd have to take into account economic considerations. So here we are. We're doing condition monitoring. Let's just think of oil sampling. And you have a trend line there that shows that over time, this trend line goes up and down. But that's just for one measurement. In practice, we have many measurements each time we take an inspection. And what we're able to do is from these measurements we take at an inspection, we're able to use a proportional hazard model to convert these measurements to one number, the hazard. So you see, from the data we get today, we can very quickly convert it to a risk factor using this equation called a proportional hazards model. And this is what a hazard model looks like. It looks awkward, but if we bring up the next animation, you'll see that this equation has two parts to it. The first part takes into account the age of the item. The second part takes into account the key risk factors, the contribution of condition information to hazard, and we combine these two bits together to calculate the hazard, the instantaneous rate of failure. And here's an example of a hazard equation dealing with oil sampling on a transmission on a haul truck engine. So what you see on the right-hand side is the symbols for lead and silicon. So in this example, the key risk factors were lead and silicon. And also you see on the left-hand side, 2.523, and that's the value for beta. And as Rodrigo mentioned, that's the shape parameter of the Weill distribution. And if you see that number being bigger than 1, then we know that age is an important risk factor. So age, iron, and lead are the risk factors for this example. And the other point that's important is I've highlighted in the bottom, constants are estimated from the data. So this is very much site-specific. It's for your equipment in your operating environment. The second thing we need to consider are what we call transition probabilities. How do measurements change from one inspection to the next inspection? Now, this is an example coming from real data in an organization dealing with iron in an oil sample. What this is saying, if today my oil sample measurement is between 2.5 and 5 parts per million, in 20 days' time, the chance of the equipment going from today's condition to a worse condition is 26.7%. And for example, if today's measurement is between 2.5 and 5 parts per million, the probability of being in the failed state is 4.9%, 20 days from today. Now, we're going to look at taking into account economics. Here's a chart you see that is the hazard. So we know how to get hazard from your data using a hazard model. And that hazard will change over time, possibly trending upwards. And the question in our mind is, when should we intervene? So you can tell the inspector, once the hazard gets to the first level you see on the screen, take it out of service and do a preventive change out. If the hazard level is low, then they'll do a lot of preventive work and suffer a few failures. As you increase the hazard level, you'll do less preventive work and suffer more failures. In the limit, we could do no inspections. And if you do no inspections, you simply run to failure. And we know what the cost is of running to failure. It's simply the cost of a fail replacement divided by the mean time to failure. But what's possible, and I'll show you in a minute, is how to find what the costs are for other hazard levels. So if we set the hazard level low, we know we're going to do a lot of preventive work and suffer more failures, but using our costs and mathematics, we can calculate what the cost per unit time is for that hazard level. So there's the cost to begin with. The next level up, we have a new cost, and so on. We get different costs for different hazard levels. And of course, what we're looking for is the minimum cost. And we want to know what hazard level is associated with the minimal cost. And there it is on the top graph. And now you tell the inspector, when you're doing your inspections, calculate the hazard. Once the hazard gets to that optimal value, plan to change out preventively. And so that's how we get this red, green, and yellow chart. There's our dots appearing on the chart. So what this means is that the dot is in the green zone, we're coming down the cost function. If the dot's in the red zone, we've gone past the minimum of the cost function. The best time to change out is in between the green and the red. Now, if you see this chart decaying downwards, that tells us immediately that age is also an important risk factor. So what I'd like to say is that that red, green, yellow chart overcomes many of the limitations associated with the standard approach rooted in statistical process control. So let's look at one case study now. Now, this is an example coming from wheel motors in a mining company, and they were using the standard approach, warning limits, alarm limits, and so on. And that's the rules they had. If the aluminum was less than 20 parts per million, everything was okay. 20 to 40, warning. Above 40, alarm. So these are the rules that were being used in this organization to interpret the measurements coming from the laboratory from oil sampling. Now, here's an example. Today, we've taken an oil sample, we've sent it to the laboratory, and they tell us what the answers are. They tell us that aluminum is 2 parts per million, chrome is 1 part per million, and so on. So this is the report we get back from the lab. Now, we've not just got today's measurements, but we've got measurements from the previous inspections. And by combining all that data, we're able to create that red, green, yellow chart that you see on the right-hand side. And you can see the last dot in that red, green, yellow chart says, don't replace. So that's the recommendation to the inspector. Just keep running. Don't change out the electric wheel motor. And of course, many of us in engineering want to know, but it's okay telling me to keep running, but when might I expect to have to change out the plant? So here we also can make an expectation of how long it's going to take before we get into the time where the recommendation is to replace. Now, this recommendation is a time to get into the red zone. It's not the time to failure, it's just a time to get the minimum of the cost function. And in this example, it's 1271 hours from today. So that time to go, we can think of it as a remaining useful life, but that's for an economic decision. Sometimes we're not interested in an economic decision. We just want to know, when is it going to fail? When is the item going to stop operating within tolerance specifications? And so for that, we can also calculate what we call here a conditional density function. This comes from diesel engines on board a ship, and this is for one of the failure modes. It was either cylinder linings or valves. But anyway, what it does say to us, here I am today, the diesel engine is 9,960 hours old. When is it going to fail? And that's the probability distribution of time to failure. There. So the mean life from today is 12,000 hours from today. That's the mean of the distribution. But what's important to the engineering manager is when he looks at that chart, you can see a peak appears long before the mean remaining useful life. So it lets you know while the mean is 12,000 hours from today, there's a high probability that failure can occur before then. So when the question is asked, what's the remaining useful life? It's good to know not just what one number is, but what the complete distribution is. And that's what we have here. So that data I've been looking at with you came from a company called Cardinal River Coals. It was a mining company, coal mining company. It dealt with electric wheel motors. We had data from a fleet size of 50 of them. And of these 50 wheel motors, there are 12 measurements they were taking. But the important measurements was the measurement of iron and sediment. So these were the two key risk factors. And we were able to demonstrate that if they used this red, green, yellow chart, compared to present practices, costs would have been reduced by 22%. Now, let me summarize by indicating the principle of this CBM optimization. On the top left-hand corner, you see a box that says age data and condition monitoring data. So to get that red, green, red, and yellow chart, we need data from your organization. The data we need is when does the item go into service, when does it come out of service, and why does it come out of service? And you do maybe all changes in between installation and removal. and also need condition monitoring data. Now, most companies have a lot of condition monitoring data, and the age data often comes from your work orders. Just to finish off, there's a note at the bottom of that slide that says all the tools in the analytic toolbox, which you can think of as a software engine, they're all in the public domain. It was all done by research students, it's all published, and so it's all available in the public domain. Now, when we started our research in collaboration with companies, we developed a toolbox ourselves to be used by companies who funded the research work. And the toolbox we developed, we call it EXACT. And I've just got some logos there of some of the companies that paid money to the university to support the development of a research team who could develop the toolbox called EXACT. So I want to give acknowledgement to these companies. And I'm sure some of you maybe work for some of these companies and certainly know of them, especially mining companies. And we've had great collaboration with industry. And I know that Professor Rodrigo also worked close with industry. And this is a quote I'd like to just read to you. It's from my project director, Dr. Dragan Banjevic. She said, "There's no better place for good ideas for theoretical research than trying to solve real world problems posed by the daily life of engineers. Most of the time, the problem does not fit available models, or the data does not follow typical assumptions. You try hard to solve the problem. You find a way. Then you get excited. And then you generalize the problem. And this leads to new theories and plenty of research." So we've had wonderful collaboration with industry, and lots of research students doing higher degrees. And I want to just stress this point from Dr. Banjevic. Thank you.